Hello and welcome to our lesson on solving trig equations with half or double angles. So we're going to start off by looking at the half angles, and to hopefully help you understand the concept that's going to be happening here, we're going to start by looking at a couple of graphs. And I'm hoping this first graph you recognize. So this would be our sine wave, the parent form of our sine wave, that one cycle happening from 0 to 2 pi. So that's the equation for y equals the sine of x. And then in our previous topic, we talked about, well, what if I wanted to solve for the sine of x equal to 1/2? Obviously, several ways to do this. Easiest way, probably going to the unit circle and looking for where we have angles where the sine of the angle is 1/2. Or we said in, again, the previous topic that if we graphed both sides of this equation, the intersections of the two graphs would show us our solution. So that's what I've done in the picture. I have the sine wave graphed in blue, and I have y equals 1/2 graphed there in red. And so these two intersections show us the same thing that the unit circle would show us. They show us that the sine of pi over 6 is going to be equal to 1/2, and that the sine of 5 pi over 6 is going to be equal to 1/2. Okay? So nothing too earth-shattering there, but now let's look at where we're going to be going. The next picture, this is still a sine wave, but this is only half of the cycle. So if I only have half of a cycle from 0 to 2 pi, that means that b is equal to 1/2. So our equation would be y equals 1/2, sine of 1/2 x, or I could call that the sine of x over 2. That is the half angle. So the sine of half of an angle. Now, again, if I wanted to solve this graphically, this is really simple. If I wanted to see where is the sine of my half angle going to be equal to 1/2, I graph the half angle, done, in blue, and I graph y equals 1/2, done, in red. I find the two intersections, and very clearly I see that my angle is going to be pi over 3, and my second angle is going to be 5 pi over 3. Okay, now if I have graphing as an option, fine, piece of cake. But what if we need to be able to do this algebraically, which is the case? How do we do this by hand? Well, when we're looking at the unit circle, which would have been a great option to use here, the unit circle doesn't have the half angle. It doesn't have the half cycle, right? The unit circle has one full cycle happening from 0 to 2 pi. So what we want to think about is, well, the half of a cycle that we're looking at on the unit circle, that's going to happen in half of the time that it happened in our half angle graph. So that top half, that first half of the cycle that's graphed from 0 to 2 pi in the second graph, that happens in 0 to pi in our first graph. So if I want to use the unit circle, I just need to think about where I'm looking. If I want to look at half of the cycle, which is what the half angle graph is saying, look at half of a cycle, let me look at the half of the cycle from 0 to pi instead of 0 to 2 pi. So when we go to solve, that's the first key. We're going to take our restricted domain and we're going to divide it by 2. It should be divided by 2. So normally we're saying, okay, let's just look over the interval from 0 to 2 pi. Well, if it's a half angle, let's just look over 0 to pi instead. So whatever the interval is, we're only going to need half of that to capture the half of cycle we're looking at with the half angle. Okay, now the second thing is, how do I take the solutions, right? The solutions that I'm going to get over here, how do I take those solutions that I'm going to get for my unit circle and find the actual solutions that I want for my half angle equation? Well, there's a nice connection between the solutions that are happening here and the ones that are happening here. So the first solution at pi over 6, if I take that solution, that first one at pi over 6, and I double it, multiply by 2 over 1, I get 2 pi over 6, and guess what that reduces to? It reduces to pi over 3. Again, that's what I see here. Or if I take that second solution, which was 5 pi over 6, and I double it, then I'm going to get 10 pi over 6, and 10 pi over 6 reduces to what I have over here, which is 5 pi over 3. Okay? So I don't know if this is making 100% sense yet, but we're going to take our domain, and we're going to divide it by 2, because we're only looking at half of a cycle, and half of a cycle in the unit circle is going to happen in half of the time. So we're going to divide that time, that period, by 2. And then we're going to solve using a little bit of substitution. This will make sense when it comes back in just a second. We're going to let theta equal x over 2. So we're going to replace the half angle in our equation with the theta, and then it's going to look like a normal equation. And let's just solve it for theta like we normally solve. And then once we've solved for theta, but that's not really what we're trying to solve for. So then we will replace theta with what it replaced. So we'll go back and replace the theta with the x over 2 that it replaced. And that's going to help us find the solutions for x, which is going to be the goal to begin with. So if I want to solve for x now, and it's going to be divided by 2, I have to multiply by 2, which is exactly what we did to go from here to here. We took the angles and multiplied them by 2. So to find the solutions for x, each angle will be doubled. Alright, so let's try this out. First, it says solve on the interval from 0 to 360. Because this is a half angle, I'm going to cut that normal interval in half. I only have to look at half of a cycle. That's going to happen in half of the time. So if I take this and divide by 2, then the interval I'm going to be looking at is actually going to be from 0 to 180 degrees. Alright, now when I solve this, I'm going to use a little substitution. I'm going to replace the x over 2 with theta. So I'm going to let theta equal x over 2. So when I rewrite this, this is going to be 2 times the cosine of theta equal to 1, because I have a lot of experience of solving in this format. So from here, all I got to do to solve is divide both sides by 2. Now my cosine of theta is all by itself equal to a half, and I can go to my unit circle. Okay, my unit circle is going to show me exactly where I have a cosine value of 1/2. Now remember, I'm only looking from 0 to 180 degrees. So here, in that window, that's where I'm going to have half of my cycle. I have cosine equal to a positive 1/2 at pi over 3. That's the only angle we're looking at, or we're in degrees, so let's say 60 degrees. Okay, so back here, that's the only answer I'm looking for theta. We're going to say theta, if I get my pen going here, is going to be equal to 60 degrees. Now, technically, that's a solution for theta. I don't really want to solve for theta, but that's how I have to do it to use my unit circle. Okay, what I want are my solutions for x. So I introduced theta, now I'm going to get rid of theta. Theta replaced my x over 2. Now I'm going to replace theta with what it replaced. So I'm going to get theta back out of there. I'm going to put x over 2 back in. So instead of theta equals 60, I'm going to say x over 2 equals 60 degrees. And then again, to solve for x, if it's being divided by 2, all I have to do is multiply. So if I multiply by 2 here and multiply by 2 here, that's going to cancel, and I'm going to see my value for x is 120 degrees. That's going to be my solution over that interval from 0 to 180. And this will make sense if you plug it back in as well. You can always check your answers by plugging back in. If you put 120 back in here and divide it by 2, then you're looking at the cosine of 60. The cosine of 60 degrees is a half. Multiplying a half by 2 would take us back to the 1. So you could always plug your answers back in to check them. Okay? So that wasn't too terrible, I'm hoping. And you can also, remember, use your graph to make sense of this, but let's try a second one. We're going to solve this one on the interval from 0 to 2 pi. So we're back into radians, but remember, we're looking at a half angle here. So a half an angle means half of a cycle. So instead of 0 to 2 pi, we're going to cut this in half, and we're looking at only an interval from 0 to 1 pi. Okay, so the half of a cycle happens in half of the time. Now let's solve this first with a theta in there instead of an x over 2. So I'm going to let theta equal x over 2 and rewrite this. It's 2 times the sine of theta now minus a radical 2 equal to 0. And this one's pretty easy to solve. Again, we've had a lot of practice with this. First, we're going to add the radical 2 over, and then we're going to divide both sides by a radical 2. So now we're going to be looking for where the sine of our angle is equal to radical 2 over 2. And remember, we're only looking from 0 to pi. We want a half of a cycle, so half of our unit circle. So from 0 to pi, where is our sine equal to a positive radical 2 over 2? That was what it was, right? Yes. So where is our sine equal to positive radical 2 over 2? That's going to happen here, and then it's also going to happen here. So I have two angles. One's going to be pi over 4, and one's going to be 3 pi over 4. So back to this, I'm going to say that theta is going to be equal to pi over 4, and that theta is going to be equal to 3 pi over 4. And if I was solving for theta, I would be done here. However, I'm not solving for theta, I'm trying to solve for x. So now I want to put x back into the picture. Since I let theta equal x over 2, since I replaced x over 2 with theta, now I can replace theta with x over 2. So I'm going to say x over, let me go back to blue. Sorry. We're going to say x over 2 equals pi over 4. And over here, same thing, x over 2 is equal to 3 pi over 4. So if I want to solve for x, I got to get rid of the divide by 2, which means I'm going to multiply both sides by 2. That's going to cancel, and x is going to be all by itself equal to 2 pi over 4, which is going to reduce to pi over 2. And then the same thing over here. If I multiply by 2 and multiply by 2, those are going to cancel. X would be all by itself equal to, that's going to be, let's see, 6 over 4, but that's going to reduce to 3 over 2, so 3 pi over 2. And those are going to be my two solutions in that interval. Okay? Hopefully this is making a little bit of sense, right? We want to cut the domain in half because we're only looking at half of a cycle. And then we put theta in there, solve for theta, because that's a process we're used to doing. And then just put in the x back that we were trying to solve for in the beginning. So we do a little bit of substitution, right? Divide our domain in half, do some substitution, then double our solutions, and we're done. Alright, now the similar concept is going to happen here when we're trying to solve with a double angle. So first, again, let me show you the graph. If I, again, I'm comparing here, so y equal to the sine of x, and solving where the sine of x is equal to a half. Again, I said solutions would be pi over 6 and 5 pi over 6. Okay? Now, over here we see what's happening in this graph is instead of one cycle, I have one here, and I have a second one here. So not a half a cycle, but 2 cycles. That means b is going to be 2 in this one. So if b is equal to 2, then y is equal to the sine of 2x, a double angle. So what happens when I go to solve with my double angle? So the sine of 2x equal to a half. Again, with the graph, this is easy. I can see the 4 intersections here are going to be the 4 solutions. So x in this one is equal to, we have a pi over 12, we have a 5 pi over 12, we have a 13 pi over 12, and then I have a 17 pi over 12. So graphically, again, this is simple. But what if I didn't have the graph, right? What if all I had was my unit circle, my one cycle from 0 to 2 pi? How can I use that unit circle to still produce those 4 solutions? Well, now, since I have 2 cycles happening in here, I have to try to use my unit circle to get 2 cycles. So if I wanted to get 2 cycles out of the unit circle, one happens from 0 to 2 pi, I'd have to go from 2 pi to 4 pi to get a second cycle, which means I have to go around the unit circle twice. So instead of going from 0 to 2 pi, I would have to go from 0 to 4 pi on my unit circle to get 2 cycles, which means my domain is going to double. So instead of cutting my domain in half because I have a half angle, if I have a double angle, I want to take my domain and double it. So my domain should be doubled. Again, 2 cycles on the unit circle are going to happen from 0 to 4 pi instead of 0 to 2 pi. And then we just got to see the connection between the solutions. So if I went around the unit circle twice, okay, this would be the first solution here and the second solution. And if I went around the unit circle again, I would have to add 2 pi to the pi over 6 to get the next solution, and I'd have to add 2 pi to 5 pi over 6 to get the next solution there, right? Those are solutions plus 2 pi n times while we're going a second time around. So if I added 2 pi to pi over 6, 2 pi is technically 12 pi over 6. So the 12 and the 1 would be 13 pi over 6. That would be the next solution. Okay, and then over here, again, if I added 2 pi, I'm adding 12 pi over 6 plus the 5. That would be 17 pi over 6 as my next solution. Now, can we see what's happening? Now that I've gone around the unit circle twice, I have 4 solutions here, just like I have over here. And these are pretty similar looking, except what's happening is if I divide this by 2, instead of doubling like we were over there, divide by 2, I'm going to get the pi over 12. Divide this by 2, and I get to 5 pi over 12. Divide this by 2, and I get to 13 pi over 12. And divide this by 2, and I'm going to get to 17 pi over 12. So we want to double the domain and then divide the angles by 2. Exactly the reverse of what we did a few minutes ago, where we cut the domain in half and then we doubled to solve for x. Here we're going to double the domain and then cut the angles in half to solve for x, and that will make a little more sense too when we actually do the solving. So we'll do some substitution again. We're going to let theta replace our double angle and solve for theta because that's easy. We've done that a bunch. And then once we've solved for theta, we're going to get rid of it. So then we'll replace the theta with what it replaced, which was that 2x. So if I want to solve for x here, and it's being multiplied by 2, again, I'm going to have to divide 2 to get the angles that I'm actually looking for. So each angle is going to be divided by 2. All right, so let's try it. Over the interval from 0 to 2 pi, that's normally what we're doing, but here it's a double angle, so I want to double my domain. So I'm actually going to be looking from 0 to 4 pi. I have to lap around 2 times to get the double. Okay? So when I go to solve this, again, I'm going to replace that double angle because it's looking a little strange. I'm going to let theta equal that double angle. So when I rewrite this, I'm looking at 3 times the tangent of theta equal to radical 3. So I'm going to divide the 3 over. So the tangent of theta is going to equal radical 3 over 3. And I feel like I may have made a typo on this problem. Radical 3 over 3, where's our tangent going to be equal to radical 3 over 3? Why am I having a moment here? Am I losing my stuff? Tangent. Oh, it's sorry, I am having a moment. Alright, so we want to figure out from our unit circle where our tangent of our angle is going to be equal to radical 3 over 3. It's, I'm not used to looking at, or haven't looked at the rationalized form. I don't know. Don't mind me. Okay, so we're going to actually have to go around the unit circle twice, but let's get it in one lap first. Where am I going to have a tangent of my angle equal to a radical 3 over 3? So I know it's not going to happen here because that's going to give me 1. It's going to be one of these two, right? Am I going to divide my, remember, tangent sine divided by cosine. So if I take my 1/2 in this case and divide it by radical 3 over 2, I end up with 1 over radical 3. Well, that doesn't look like what I have here, but if I rationalize, then it will. So when I multiply by radical 3 over radical 3, I get radical 3 on the top and I get 3 on the bottom. So it is going to, in fact, happen when I have a radical 3 first and then a 1/2 next. So that's a sine of 1/2 divided by a cosine of radical 3 over 2. And I want it to be positive, so I know one of my angles is going to be pi over 6. And then I don't want to use this one because that's a positive and a negative, but I will take this 7 pi over 6 because a negative is going to make a positive, so this will also get me that same thing. Okay, so that radical 3 over 3. And again, I don't want to use this one because that's going to produce a negative. So that's just in one lap of the unit circle. So I've got pi over 6 and I've got 7 pi over 6. Excuse me. But remember, our domain is not 0 to 2 pi anymore. It's not one lap. It's 0 to 4 pi, so I have to lap around again. Okay? So if I added 2 pi here, which again is like adding 12 pi over 6. Then that 1 pi plus that 12 pi is going to give us 13 pi over 6 for that next angle. So this is going to be one of them, and this is going to be the other one when I take the second lap. And the same thing for 7 pi over 6. If I add 2 pi to that the second time I lap that around, or again add 12 pi over 6, the 12 and the 7, that's going to give me 12 and 7, that's going to give me 19 pi over 6. Okay? So I have these two angles, and then I lap around again, and I get the two other angles. So because I'm not going to be going an infinite number of times, which actually would have made this problem a little bit easier, I need those four distinct angles. Okay, so let me go back here. We said that this is going to happen when theta is equal to pi over 6, and then 7 pi over 6. And then I added 2 pi to this to get to my next angle. So 12 pi plus the 12 pi over 6 plus the 1 pi over 6 made the next one 13 pi over 6. And then I added 2 pi to this one to get the next angle. So adding 12 pi over 6 plus 7 pi over 6 gave me 19 pi over 6 on this one. And maybe I should change colors because I used green already. Okay, how about gray? Add 2 pi to this, and that's where I get the 19 pi over 6. Okay, so far, I hope. So those are my solutions for theta. And if I was just solving for theta, I would be good. But remember, I'm actually trying to solve for x. So I let theta replace 2x. Now I'm going to replace theta with, again, what it replaced, which is the 2x. So now I'm going to go back and say that 2x has to equal all of these things. Pi over 6, 7 pi over 6, 13 pi over 6, and 19 pi over 6. So if I want to solve for x and it's being multiplied by 2, what do I have to do? Well, I got to divide everything by 2. Divide by 2, divide by 2, divide by 2. Dividing by 2 is multiplying by half, so that 2 is going to end up in all of those denominators. So my solutions for x will be pi over 12, 7 pi over 12, 13 pi over 12, and finally 19 pi over 12. And those would be my four distinct solutions over that interval. Fun stuff, right? Good thing I gave you a lot of space for that. Okay, so let's try another. Okay, let's try the next one. Now notice on this one there isn't a domain restriction. So typically what happens when we find a solution is we just like add 2 pi n to that restriction, right? So if that were the case, then whatever that restriction is would be, or whatever that is, it's going to take into, I don't know if we don't have to worry about it, I guess is what I'm saying just now. Okay, so let's not worry about that just now. Let's go ahead and do the substitution. We don't have a restricted to domain to worry about, so let's worry about our equation. So first thing I'm going to do is, since I don't have a domain to double, is I'm going to use some substitution. Let theta equal that double angle. So 4 times the sine squared of theta is going to be equal to 1. So I divide that 4 over, which means the sine squared theta is going to equal 1/4. And then take the square root of both sides, so that my sine of theta is going to be equal to a positive or negative. The square root of 1 is 1, and the square root of 4 is 2. So I'm going to be looking for where the sine of my angle is equal to a positive or negative 1/2. And I just made a big mess of my unit circle, so let me fix all this. Where is the sine of my angle going to be equal to a positive or negative 1/2? So sine being a positive 1/2 here, sine being a positive 1/2 here, negative 1/2 here, negative 1/2 here. So if I was going to say this concisely, I'm looking at pi over 6 plus pi n times, and I'm also looking at 5 pi over 6 plus pi n times. Okay, so hopefully we're okay with that. That's nothing new. So at pi over 6 plus pi n and 5 pi over 6 plus pi n. Those will be my solutions for theta. So theta is going to equal pi over 6 plus pi n times, and theta is going to equal 5 pi. Oh, let me write this over here. Theta is also going to equal 5 pi over 6 plus pi n times. Now, again, if we were solving for theta, we would be done. But we're not solving for theta. We let theta replace 2x, so now let's replace theta with 2x. So this means 2x is going to equal pi over 6 plus pi n. And then again, 2x is going to equal 5 pi over 6 plus pi n. So if I want to solve for x, I have to get rid of the multiply by 2, which means everything is going to be divided by 2, including the pi n. So divide everything by 2, and that means x is going to equal, again, dividing by 2, that's multiplying by a half. So this is going to be pi over 12 here, plus pi over 2 in front of n, or pi n over 2. It's 90 degrees, if the degrees make a little more sense for you. And then over here, it's going to be 5 pi over 12 plus, well, I'm getting a little sloppy. Let me try that again. 5 pi over 12 plus pi over 2n. So every 90 degrees, these things are happening. All right, so those would be our solutions. In the infinite form, again, we didn't have a domain restriction to worry about, so we add on the 2 pi n, whatever it is, and it ends up getting cut in half in this case. And the same thing would happen with the half angle. We would double here, we just cut in half to solve for x, but if you don't have a domain restriction to worry about in the beginning, then you don't have to worry about cutting it in half or doubling it in the beginning. But if you do, then you want to make sure you're using that to get the distinct angles, and then cut them in half or double depending on which types of angles you're looking at. So if it's a little confusing, it takes a little bit of practice. Don't worry, you can always remember use the graphing feature to solve. That will kind of give you direction on how many solutions you're looking for before you tried to solve by hand. Or if you just wanted to verify the solutions after you got them, then by all means, use a calculator, plug them back in. Alright, so I think you've got enough to get going, but as always, if you need some extra help, please reach out. Until next time, take care.